So when we balance our oxidation reduction reactions, we have to watch the charges. So there's two ways that we can do this, two types of balancing processes that we can do this to identify the charges. Our process that we do typically ends up creating an acidic environment for our redox reaction, which might be true. Our lead acid batteries for our car are in an acidic environment. But the alkaline batteries that we use in our flashlights are, well, alkaline. So what we do is we balance it in an acidic environment. This is just a technique that makes it easy for us. It might be neutral, it might be acidic, but it won't be basic. And then if it's acidic, then we neutralize the acid later on to turn it into a basic reaction if necessary. So the first method, the oxidation number method, is probably the simpler of the two methods, as long as you keep track of the numbers properly. So what we do is first is we identify all the oxidation numbers. We identify what is oxidized and reduced. And then what we do is we identify how many electrons are transferred for each of the for each reaction, for the oxidation reaction and for the reduction reaction separately. So if oxidation number goes from +1 to +3 for oxidation, that's 2 electrons transferred. If it goes from +6 to +3 for the reduction, that's 3 electrons transferred. And then between the two reactions, we find a common factor, so the same number of electrons are transferred. So if we have 2 and 3, what we're going to do is find the common factor of 6, 2 times 3. Then we multiply everything in each half reaction, so we have to make sure the half reaction okay. I seem to be missing a step. So, what we do, we identify the number of electrons, we find the common factor, but we now have to create the half reactions. So the half reactions are going to take each species is going to separate find all these species that are participating in each half reaction. So for each half reaction, we're going to have the initial and final species that are changing the oxidation numbers. We're going to have the initial and final species for both the oxidation reaction and reduction reaction. So then we have to multiply each part of the half reaction that we can identify by the appropriate coefficient, so we end up with the same number of electrons for both reactions. So we have to identify all the main species. We're not going to worry about oxygen or hydrogen when we do this. But the other elements we have to be able to identify and balance. So we have to assign them to one of these two half reactions. Then to balance oxygen, we're going to balance oxygen with water. So if there's more oxygen on one side, we put water on the other side to balance the oxygen. Water, of course, has hydrogen. So if we have, after we balance the oxygen, we're going to balance the hydrogen using H+, using acid, H+. And then after we balance our acid, we should have a balanced reaction. So what we need to do is check to make sure all the elements are balanced and that the charges are balanced. Everything should be balanced right now. If they're not balanced, we go back to the beginning and start all over again. If this will obviously leave us with an acidic solution, since we're putting in H+ acid. So if we are dealing with something that we know is going to be basic, like an alkaline battery, we have to make it alkaline. And what we do, the number of excess hydrogen on one side of the reaction, we're going to put the same number of hydroxide on both sides of the reaction. So that way we're going to turn all of our H+ into water. So H+ plus OH- gives us water. So we turn all our H+ into water. the other side of the reaction is going to end up with hydroxide on it. And now we check to see if there's water showing up on both sides of the reaction. If there is, we take the same number of water off both sides of the reaction until water only shows up on one side of the reaction. The other method is the half reaction method. What we're going to do is completely separate the reaction into half reactions first, balance those, and then add the two half reactions together. So we have to start off the same way. We start off assigning oxidation states to each element, identify what's being oxidized, what's being reduced. Now we're going to pull these into separate reactions. So all the main elements except for oxygen and hydrogen should now be assigned to one of the two reactions. So for each half reaction now, we're going to balance all the main elements, except don't worry about hydrogen and oxygen. After all the main elements are balanced, then we're going to balance oxygen using water. And we balance hydrogen using H+, hydrogen ion. So everything should be balanced now except for charge. So we're going to balance the charge using electrons. So one of the reactions should show electrons as a reaction. The other reaction should show electrons as a product. Now we look at the number of electrons on both half reactions, and we have to find a common factor. So we find what factors we need to multiply each half reaction so we get the same number of electrons for both reactions. We multiply these half reactions by those numbers, multiply all the components of the half reactions by those numbers, and we'll end up with balanced half reactions with the same number of electrons. Now we can add them together, because when we add them together, the electrons will cancel off. We'll be left with no electrons. Then we check to see if there's anything else that is common for both reactions, especially water or hydrogen ion. And then we should end up with a balanced reaction that's balanced for all the chemicals present and for any charges present. And again, this will either be a neutral or acidic solution. So if we need a basic solution, we add hydroxide equal to the number of hydrogen ions present. But we add the hydroxide to both sides of the reaction. So one side will neutralize hydrogen ion and form water, and the other side, the hydroxide, will remain. If we have water on both sides of the equation, we subtract that off to give us our overall equation. So, to go through this now, if we have a reaction, we have dichromate ion reacting with nitrite to give us chromium 3 ion and nitrate. Our first step is to identify the oxidation states, so we can identify what's being oxidized and reduced. So we identify oxidation states. So some will be easy. So in the dichromate ion, we have no rule for chromium. We have a rule for oxygen. In a compound, it's going to be generally -2. So we assign -2 to the oxygen. Now we use the summation rule that all the oxidation states adds up to the ionic charge. So 2 times the unknown chromium plus 7 times the -2 all add up to -2. So you write down the equation, solve for the chromium, and you'll find out that chromium will be a +6. We do the same process for the nitrate. Oxygen is assigned -2. Then we use the summation rule. 1 nitrogen plus our 2 -2 oxygens will add up to a -1 overall charge. That means our nitrogen has to be a +3. Chromium 3+ is just going to be 3+, the charge on the ion. For nitrate, again we assign -2 for the oxygen. 1 nitrogen plus 3 -2 oxygens adds up to a -1 overall charge, which means that the nitrogen ends up being a +5. So we look at this, we see our chromium going from a plus 6 down to a plus 3. So chromium is being reduced. We see our nitrogen going from a plus 3 to a plus 5. The nitrogen is being oxidized. So this example is using the half reaction method. So we separate out those. We take the chromium by itself, the reduction, and with the nitrogen by itself for the oxidation. Okay, so our first step is going to be balance all the elements except for hydrogen and oxygen. The nitrogen 1 is already balanced for nitrogen. Chromium is not balanced on the reduction reaction. So on the product side, we need 2 chromiums to balance the 2 chromiums on the reduction side. Now we want to balance our oxygen using water. So for oxidation reaction, we had 3 oxygens as a product, but 2 for the reactant side. So we put a water on the reactant side to give us 3 oxygens. For our reduction reaction, we have 7 oxygens on the reactant side, none on the product side, so we add in 7 waters on the product side. Next step is that we're going to balance our hydrogen using H+. For the oxidation reaction, we have 2 hydrogen for the reactants and none for the product, so we're going to add 2 H+ for the product. For the reduction reaction, we had no hydrogen for the reactants, but 7 waters, which is 14 hydrogens on the product, so we add in 14 H+ on the reactant side. So our final step of the half reactions here is to balance the charge using electrons. So we look at the charge on the oxidation reaction. We have a -1 for the reactants. For the products, we have a -1 plus 2 +1s. That's a total overall charge of +1. So we have -1 left, +1 on the right. A change of 2 from negative to positive. That's 2. So we need 2 electrons on the right. 2 electrons on the right give us an overall charge on the right of -1, which matches the -1 on the left. For the reduction reaction, we have a -2 for the chromium. We have 14 pluses for the hydrogen. Add them together, and that gives a total of +12. On the product side, we have 2 times the chromium 3+. That means we have 2 times 3 is 6. We have a +6. So we have +12 on the left, +6 on the right. So we add 6 electrons to the left side. That brings the total charge on the left side down to a +6, which now matches the right side. So now we have 2 balanced half reactions. We check the number of electrons. We see that we have 6 for the reduction reaction, 2 for the oxidation reaction. We can use a common factor of 6 by just multiplying by our oxidation reaction by 3. So we multiply the whole oxidation reaction, every component, by 3. After we do that, we'll have 6 electrons for the oxidation, 6 for the reduction. Now we're ready to add the 2 reactions together. We add the 2 reactions together. We're going to have 6 electrons on both sides of the reaction. They cancel off. We check through for any other duplicate species, such as water. We have 3 waters on the left, 7 on the right. So we subtract 3 from both sides. That will give us only 4 on the right side, the product side. We have 14 hydrogen ions on the left, 6 on the right. We subtract off 6. That will leave us 8 hydrogen ions on the reactant side. And now this will give us our overall reaction. This is in acidic solution. If we ask for acidic solution, or if we don't specify, this is the answer that we need. If we ask for a basic solution, do I go through that? Reaction ends. I'm not showing the basic solution, but if we wanted to make this into a basic solution, what we would do is add 8 hydroxides to both sides. to cancel off the 8 hydrogen ions on the reactant side. That would give us 8 waters on the reactant side, 8 hydroxides on the product side. And then we subtract off 4 waters from both sides of the reaction, so we don't have water on both sides of the reaction. And that's it for this chapter.